Welcome to a physics class on refraction of light. In today's class, uh, we will try to learn about what is refraction, laws of refraction, and then we will try to see the refractive index and then some related facts about the refraction of light, like that of your total internal reflection. Okay, such thing will be discussed here. Okay, let's see one by one. Now, refraction of light is a phenomenon of the change in the path of light as it travels obliquely from one transparent medium to another having different optical density is called refraction of light. Or you can also simply define this refraction of light as a phenomenon of light in which an oblique light ray bends when light travels from one medium to another transparent medium having different optical densities. Okay, it is just as the diagram shown here. The angle between the incident ray and the normal at the point of incidence, we call it that as angle of incidence, and the angle between the refracted ray and the normal at the point of incidence, we call it this angle as the angle of refraction. Now let's see the actual observation that we have seen from the air to water. Okay, if you immerse a pencil inside the water, then you might have seen the pencil as banded. That bending of the pencil when immersed inside the water, that is due to the refraction of light. It will be seen in this manner. See, got it? This is the your eye. Your eye is somewhere here, and you may see that this pencil seems to be banded here, and you may think that the length of the pencil inside the water is shortened. Okay, so let me show you again the way it is to be seen. Okay, the part, I mean the light part. Okay, it will be seen in this way. So the light coming out from the tips of the pencil inside the water, okay, that comes to outside air, it will be along this part and it will be banded. This is denser medium and air is this rarer medium. So when light travel from denser to rarer, it will bend away from normal. Okay, so this observer, okay, may see the pencil, the tip of the pencil not here, rather it may be seen somewhere here. Okay, when you move backward like this, the light part which is coming toward the eye is this one. So to him or to the observer, it may be seen somewhere here raising. Okay, yes, let's see another one, the similar one. Okay, fish is inside the water, and to a person on the lane it may be seen somewhat shallow, that means somewhat closer to from the surface of the water. Okay, it will be seen in this way. Okay, so this is nothing but some bending or distortion of the light part when light travel from one medium to another medium having different optical densities. Now let's see about the laws of refraction. Suppose we are taking two media. Okay, one is rarer medium, another is denser medium, and this denser medium is placed inside the rarer medium. So when it enters the light ray, I mean it enters from the rarer medium to denser medium, and then it emerges out from the denser medium to the rarer medium again. Okay, so angle between the normal and the incident ray, we call it as angle of incidence. Angle between the normal at the point of incidence and the refracted ray, we call it that angle as angle of refraction. And the angle between the emergent ray and the normal at the point of emergence, we call it this angle as angle of emergence. It is denoted by E. But in this case, as these two opposite surfaces are parallel, so what happen, your angle of incidence will be equal to angle of emergence. Got it? Let's see the light part. Okay, in the next slide it will be seen there. let's see the motion of the light part. Let's see, this is the denser medium of having absolute refractive index mu. Now when this is denser medium, and the upper one is a rarer medium, and downward is also the rarer medium. Okay, so when light ray it passes here, it will bend in this manner. Let me show you again, observe it carefully. Okay, it will be passing like this, in this manner. So what happened, let's see how much it is the angle of incidence, angle of refraction, and then angle of emergence. Let's see, these are the normals. Okay, these are the normal at the point of incidence and at the point of emergence. Let I be the angle of incidence and R be the angle of refraction. As these two normals are parallel, these and these are not parallel, what happen, this may be taken as what your transversal, and you can take it that these two angles are what, alternate angles. So alternate angles are equal, so your angle of refraction, okay, from rarer to denser, that will be equal to the angle of incidence for the light ray to move from denser medium to rarer medium, denser medium to rarer medium. So this angle will be now known as angle of incidence for the refraction from denser to rarer. Okay, yes. So now let's see the laws. Okay, the laws of refraction one after the another. Now before going to that, now this constant mu is known as refractive index of this particular denser medium, okay, with respect to the rarer medium. We generally denote it like this mu with respect to 1, or it may be also denoted by mu to 1, like this. In some textbook it may be written as n to 1 also, or it may be denoted by n to, okay, n to 1, like this. Okay, so n to 1, that means this is a refractive index of the second medium with respect to the first medium. Now in our case, the second medium is denser medium and the first medium is a rarer medium. This medium is taken as a first, and this medium is taken as a second. Wherever the incident ray lie, we take it that as the first medium, and wherever the refracted ray lie, that medium is taken as the second medium. Or if you simply write as mu2 like this, that means we do not have any first medium. Then this first medium, if there is nothing written here in the for the first medium, then it is understood that this first medium is vacuum. Okay, if it is vacuum, then no need of writing vacuum like this, rather it will simply write as mu2 like this. This means this is called as absolute refractive index of the second medium. That means this is the refractive index of second medium with respect to what, vacuum. Got it? So for vacuum we do not write it generally, so it will be written only like this. If it is written like this, that means it is what, absolute refractive index of second medium. Okay, so whatever it is written here in this is nothing but this is a refractive index, rather absolute refractive index of the denser medium if it is written here like this. Okay, so this is the angle of incidence, okay, and I is the angle of incidence and R is the angle of refraction. So we are going to relate with this angle of incidence I, angle of refraction R, with this of what, refractive index in the laws of refraction. The first law states that, let's see about the first law. The first law states that angle of the incident ray, the refracted ray, okay, lie on the same plane. That means if the refracted incident ray lie on the plane of this screen, then the refracted ray should also lie onto the plane of this screen. If incident ray lie on the screen and the refracted ray will not move in another plane, okay, it will not be like that. Okay, so the first law of refraction states that angle this incident ray, refracted ray, and the normal at the point of incidence all will lie on the same plane and meet at a point, that means at the point of incidence. Okay, and the second law of refraction states that sine of angle of incidence to the sine of angle of refraction always bears a constant ratio. That means sine of angle of incidence to the sine of angle of refraction. This will be always a constant, and this constant is nothing but it is known as refractive index of this second medium with respect to the first. Got it? Refractive index of second medium with respect to the first, and this will be always constant, okay, provided that this pair of media remains same for every angle of incidence. Okay, if you change this angle of incidence, correspondingly angle of refraction will be also changed, and if you take it the ratio of those two, sine of angle of incidence and sine of angle of refraction, then it will be always constant, this mu 2 1. That means refractive index of second medium with respect to the first medium. If you take it, suppose somewhere here angle of incidence, okay, different angle of incidence, there will be a corresponding different angle of refraction also. So if you take it those sine, then this will remain constant. That is the meaning. Got it? So that is known as what? Second law of refraction, and this second law is also known as Snell's law. Okay, yes, let's see. These are the laws of refraction. Okay, first law it is also here given here, and the second law here. Whatever I have said, it will be all coming here. Okay, and when we write it this mathematical form of the second law of refraction, then it will be in this way. Mu is equal to, this mu means nothing but this is the mu of the second medium with respect to the first. Okay, if it is not written, that means there in the diagram it is written as the denser medium as mu. So that means this is the refractive index of the denser medium with respect to the rarer medium. Got it? So this is equal to sine of angle of incidence to the sine of angle of refraction. Now some points to be remembered. Okay, in refraction the velocity of the light changes, and also the wavelength of light changes when light travels from one medium to, when light travels from one transparent medium to another transparent medium having different optical densities. Okay, but in refraction this is very important. Okay, phase and frequency of light doesn't change when light travels from one transparent medium to another transparent medium, right? Now this will give you the cause of refraction. Why there is a banding of light take place when light travels from one medium to another medium having different optical densities at the interface. Okay, it is because what, this light, when light travels from one medium to another transparent medium, velocity of light changes, and because of that what happened, since light is banding. Okay, so that banding of light, it is due to what, the change in the velocity of light. So in the case of this Snell's law, that means second law of refraction, I told you that this mu 2, okay, 1, that means refractive index of second medium with respect to the first medium, that will be equal to sine of angle of incidence to the sine of angle of refraction, and this will be also equal to the ratio of the velocity of light in the first medium, okay, to the velocity of light in the second medium. v1 represents velocity of light in the first medium, and v2 represents the velocity of light in the second medium. Okay, and this can be also related with that of wavelength of light. Wavelength of light in the first medium to the wavelength of light in the second medium. You can still also relate with that of the refractive index in terms of absolute refractive index, I should say. Absolute refractive index of second medium, okay, absolute refractive index of second medium to the absolute refractive index of the first medium. Okay, like this. So absolute refractive index of second medium to the absolute refractive index of the first medium, the ratio of these two will be also equal to what, your refractive index of second medium to the first medium with respect to the first medium. Got it? Now let's see. We know that when light travels from rarer to denser, then what happens? It bends toward the normal. Why it is so? Let's see. From what, rarer to denser, if you take it this as a rarer and the second as a denser, then if a light ray like this incident on to the interface, then the refracted ray bends like this. That means it will, instead of going here, it will bend toward this normal. it will bend this side. Okay, why it is so? Let's see. Rarer means what? The velocity of light here in the rarer medium will be more than the velocity of light in the denser medium. That means what? Your V1 is greater than V2. What is this V1? V1 is the velocity of light in the rarer medium, and V2 is the velocity of light in the denser medium. Suppose if your V1, okay, is greater than what? V2, then naturally what happen? This ratio, from this ratio, okay, V1 is greater, so what happen? This ratio will be greater than 1. Okay, this ratio is greater than 1, and so what happen? In this again, sine of an angle, if angle is more, then the value of that sine of angle will be also more, right? So what happen? As this ratio V1 by V2, as V1 is greater than V2, then what happen? This ratio will be greater than 1, right? So what happen? This ratio will be also greater than 1. So sine of angle of this incidence, okay, sine of angle of incidence to the sine of angle of refraction, this will be greater than 1. That means what? Angle of incidence must be greater than angle of refraction. Got it? That is what we are having here. Got it? So what happened when that angle of incidence is greater than angle of refraction? Naturally, in that diagram, as I told you, this is rarer medium, this is denser medium, this is normal. So what happened? The refracted ray should bend. So in this case, what happened? Angle of incidence and angle of refraction, here we see that angle of incidence is greater than what? Angle of refraction. So what happened? When light travels from one transparent medium to another transparent medium having different optical densities, their velocity what? Changes. Okay, when light travel from rarer medium to denser medium, velocity decreases, but when light travel from denser medium to rarer medium, velocity increases. Okay, yes, that is what this is the the real cause of refraction of light. It is because of the change in the velocity of light. Okay, yes, let's see more about the refractive index. As I have said, so refractive index, it is nothing but this is what? Speed of light. If the first medium is a vacuum and the second medium is some another medium, then what happen? Your refractive index of that medium with respect to the vacuum, that will be known as what? Your absolute refractive index of that medium. I can write as mu m like this. Got it? So this is nothing but this is the absolute refractive index of the second medium, right? So we can write it, that formula for that absolute refractive index, as like this. Got it? Yes, we can also write this in terms of the wavelength of light also. This will be equal to what? Wavelength of light in vacuum, okay, in vacuum, to the wavelength of light in that particular medium. Got it? You can express it in this way also. Now I'm giving you some example, okay, to find the refractive index. Okay, so let's take it that the velocity of light in the vacuum is 3 into 10 to the power 8 meter per second. We all know it, this one. So index of refraction will be equal to what? N is equal to, you can either use mu or n. I told you that in some textbook, instead of using mu, they may use as small n. Okay, so don't confuse it that sir is using what? Small n, okay, for refraction, I mean for refractive index, and mu also. Don't forget it that this may be just a notation. Either you can use it mu or n. So if the first medium is vacuum, then velocity of light in vacuum will be denoted by small c, and that velocity of light in some medium will be denoted by v. Then your refractive index will be denoted by what? C by v. Refractive index of what medium? Of this medium. Clear? Yes, I will still give you some more examples. Okay, so here air is equal to the refractive index of air or vacuum, or air and vacuum are almost taken as same. Okay, right? Air means which air? Dry air, not that moist air. Okay, you can take it in this way. So if glass is equal to refractive index 1.5, that of water is taken as 1.3. Okay, yes. What does it mean? When we say refractive index of glass is 1.5, that means this is 1.5. So when you multiply it with that of 3 into 10 to the power 8 meter per second divided by velocity of light in glass, you can easily find out what will be the refractive index of velocity of light in a glass medium. It will be equal to what? 3 into 10 to the power 8 divided by 1.5. Okay, when you cancel with this 1.5 and this, it will be 2. So velocity of light in the glass, it will be 2 into 10 to the power 8 meter per second. Got it? Like that. So velocity of light decreases when it travels from the air or vacuum to the glass. Got it? Yes. So these are some examples. Okay, still you can pause this video and you can watch it. Okay, not at all much explanation about this as I have just told you, right? Yes, let's see some analogy. Okay, when light travel from the air to glass, then it comes out or emerges out to the air. Light travel from what? Air, then glass, then if it emerges out to the air again. Let's see. So bending of light will take place in this manner, right? So air rarer, glass denser, then it emerges out, so it will be bended in the same way because the first medium and the third medium both are air. Okay, so it will be moving in that parallel direction like this. Got it? Yes. So now let's see for that of this velocity of light. These are all given. So as I said that this velocity of light in air is 3 into 10 to the power 8 meter per second, but in glass it is 2 into 10 to the power 8. So when it emerges out again in the air medium, okay, when in the air medium it comes again the velocity of light which was before in that medium. Okay, from 3 it reduces to 2 into 10 to the power 8. Now it again increases. Okay, likewise the analogy can be also taken when a vehicle or a motor having axle, if it is rolling onto this paveway, now you take it that this is a cemented road or pavement and this is sand or mud, and then you can take it again this as a same medium as the cemented one. So when an axle is moving here like that along this direction, so if the vehicle is moving like this onto the pavement and then to the sand or mud, then coming out to the pavement again, then it will be in this manner as I have shown you. So let me show you again once again. Okay, so the pavement will be moving like this, it will be moving slow and it will be again fast like this. Okay, in that manner that light is also coming here, okay, with decreased velocity. Here also same thing. Okay, that is the analogy. Now let's go to the principle of reversibility. Principle of reversibility means what? When light, okay, moves in a particular part, and if it is meant to move back, then what happened? The light will have to move along the same path wherever it is coming. Okay, that is known as the principle of reversibility. So let's see, this is the rarer medium, denser medium, and then it will be coming out. Okay, but let's take it that a particular mirror is placed onto the path, okay, which is supposed to come from the rarer medium. Let's see the path, okay, like this. Okay, and let it be reversed backward. Okay, why? Because onto this plane mirror the refracted ray okay, fall onto the plane mirror perpendicular to it, so that what happened, the light will be reflected that reflected back again into the same refracted part. Okay, that means what happened, light is coming from this part, it enters like this. This is the incident ray, the incident ray comes here, then refracted ray comes here like this. So onto this part of the refracted ray a plane mirror is placed normal to it, so that what happened, the refracted, okay, the reflected ray from the mirror will be moved along this part. Okay, so this will be the incident ray, I mean the incident ray at this interface. Okay, so this interface in the denser medium, incident ray in the denser medium, then it will be refracted. So this will be the normal like this, so it will bend away from the normal. Okay, being why? Because it is the light travel from the denser medium to rarer medium. So what happened, light ray instead of moving straight like this, it will bend away from the normal, okay, like this, from the normal. So what happened, this shows that light possess the principle of reversibility, okay. So let's take it in this way. Now this is normal, so what happened, angle of incidence is I, angle of refraction is R. Now this is for the refraction from the rarer medium to denser medium, from rarer medium to denser medium, from rarer medium to denser medium. Got it? Yes. Now let's see about the next one. So if the light travel from rarer medium to denser medium, then what happen, denser medium is taken as what, a refractive index or medium B. Let's take it medium B, and the refractive index is denoted by mu. So refractive index of the second medium with respect to the first, that means we need to denote it like this, mu BA. Okay, refractive index of second medium, refractive index of second medium with respect to the first. Okay, so this will be what, equal to what, sine of angle of incidence to the sine of angle of refraction. This is nothing but your Snell's law. Okay, this is nothing but this is your Snell's law, right? Now then what happened, let's see about that of the refraction that takes place from denser to rarer medium. Okay, denser to rarer medium, denser to rarer medium. That means when light travel from here like this to the rarer medium in this way, in that case angle of incidence will be what, your I will be here and your refraction will be this one, but your angle of incidence and angle of refraction in this case it is almost same. But let's see, now we are going to write it this as what, refractive index of the second medium. Now second medium is your rarer medium, so A with respect to B, this will be equal to what, sine of angle of incidence means your angle of refraction to the sine of your angle of refraction is nothing but that will be angle of incidence, like this. Got it? So when we multiply these two, that means refractive index of B with respect to A times refractive index of A with respect to B, then this will be what, the first one is this one, so sine of angle of incidence to the sine of angle of refraction times what, sine of angle of refraction to the sine of angle of incidence. So what happened, both are same, right? This will be cancelled and it will be equal to 1. So what happened, if you want to interchange these two media, okay, B and A, if you want to interchange, then it will be equal to what, reciprocal of what, B and A, like that. This will be B, okay, this will be B and this will be A, right? So that is what, here A will be on this side, B will be on this side. Okay, let's see it. So now in this is for the refraction from denser to rarer. Okay, denser, refractive index of the second medium, that means A, okay, with respect to this first. Why? Because light ray need to travel like this. This is the first medium, we need to assume it. Why? Because wherever the incident ray lie, we call it that as a first medium. Wherever the refracted ray lie, we call it that as a second medium. So refractive index of first medium with respect to the second, this will be equal to like this. So what happened when you multiply these two equations, then it will give you one like this. Okay, that means this refractive index of B with respect to A, this is equal to refractive index of A reciprocal of refractive index of A with respect to B. Now these two, okay, this one refractive index of the medium B with respect to medium A, and the another one is refractive index of A with respect to B. Okay, both are reciprocal to each other. Why? Because the product of these two gives you 1. So that means if you want to interchange the medium, okay, that means by using refractive index of B with A or refractive index of A with B, then what happened? The product will be always equal to 1. Now, if a ray of light after suffering any number of reflections and or refraction has its path reversed at any stage, then what happened? It travels back to the source along the same path but in the opposite direction. Okay, had it been moving like this with a different, suppose there are different media like this, got it? So let's take it that this is air, okay, this is as glass, this is water, like that, air, like this. Suppose if that light part, okay, travel in this manner, like this, glass, then water, it will be little bit upward like this, then it will be again bending in this way. So that means we can write like this as in this way. Okay, so refractive index, we can write it in this way: refractive index of, say, glass, okay, or water. Let me write for water with respect to air. So you can put it any like this, okay, we can insert it one medium like this: refractive index of glass with respect to air, refractive index of water with respect to glass, like this. We can insert it, got it? This is in the, say, in between these two. That means air and water is here, so air and water should be outside. You can put any number of the medium in between like this, or rather, let me write you another one. So refractive index of, say, suppose P and Q, like this. So you can write it these as any number of refractive index, okay, refractive index. So this should be P, this should be Q. The other two n, okay, one n is Q, the another n is P, right? So you can write it like this. But whatever the media that is going to be inserted in between these two media, P and Q, you can insert it whatever you like it. If it is 1 here, then it will be 1 here, then 2, 2, then 3, 3, like this. So this refractive index of P with respect to Q will be equal to refractive index, the product of refractive index of 1 with respect to Q, refractive index of Q2 with respect to 1, times refractive index of 3 with respect to 2, times the refractive index of P with respect to 3, like that. Got it? So this is coming from where? This is coming from the principle of reversibility of light. Okay. Yes. As a natural consequences of the principle of reversibility is that the image and the object position can be interchanged. Okay. Whenever you place that object, if an image is formed at a certain distance, then if that image position is met with the object position, then the image will be formed at the position of the object. That means your image position and the object position can be interchanged. These positions, wherever such object and image are interchangeable, we call these positions as conjugate positions. Okay. Now let's see about the refraction through a glass slab. Okay, let's take it that this is a glass slab, and let's take it that the glass slab is having the thickness T, okay, and having a refractive index mu. Okay, this mu is nothing but this is the absolute refractive index. Okay, if a light ray travel like this incident onto this rarer medium, then it passes to denser medium, then it again emerges out in the rarer medium like this. So what happened? Let's take it that the normals are, okay, the normals, this is the actual part of the incident ray. Okay, the distance between the emergent ray and the incident ray, the distance means the perpendicular distance between these two, we call it this as what? The lateral displacement. Okay, so this is a normal at the point of incidence, and you will see that the angle is perpendicular here. Okay, so that is the normal. So angle of incidence and angle of emergence, okay, will be equal in the case of glass slab. Why? Because the surface are, or the opposite surfaces, wherever it incident and emerges out, the two surfaces are parallel to each other. This small d is nothing but this is the what? The lateral displacement, the perpendicular distance between the incident ray and the emergent ray, we call it that distance as what? The lateral displacement. Got it? Now let's see. This I1 and I2 R2 are the angle of incidence and the angle of refraction. Angle of incidence here, angle of refraction here. So let that angle I2 be the angle of incidence for the refraction from denser medium to rarer medium, okay, before it emerges out. Okay, then what happened, this will be taken as the incident ray and this will be taken as the what, refracted ray. Okay, the emergent ray for this type of refraction from denser to rarer, it will be taken as what, the incident ray and the refracted ray. The emergent ray will be termed now as refracted ray. Okay, and the angle between the incident ray and the refracted ray, we call it that angle as the angle of deviation. How much the incident ray had been banded, that angle we call it this angle as angle of deviation and denoted by del. Okay, so see, these are the refractive index of the denser medium with respect to the first medium. Okay, and this is what, for the refraction from denser to rarer. Okay, refractive index of this second medium with respect to the first medium. This is for this refraction. Okay, this one. So we know that from the principle of reversibility, the product of these two will be equal to what, 1, right? When you cancel it, what, this, it will be equal to 1. So that means what, this angle of incidence I1, okay, angle of incidence I1, this I1 and R1, they are not equal. Had that been equal, then this incident ray would have been passing along this, okay, it will be passing here like this. But as this I1 and R1 are not equal, what happened? But we know that this light, this normal here and this normal here are parallel. Why? Because these surfaces are parallel. So if you take it this as a transversal, then what happen, your R1 and this I2 will be same. Why? Because this is just like the transversal line in between the two parallel lines. So R1 and R2 are what, equal. Why? Because they are just alternate angles. Okay, so what happened, your R1 and I2 are same, so I1 and R2 are same, so this will be cancelled. And so what happened, your sine of I1, okay, to the sine of angle R2, this will be equal to what, 1. So this can be possible only when these two are equal, right? Otherwise it can never be equal to 1. Am I right? So what happened in the case of refraction through glass slab, what happened, this I1 must be equal to what, R2. I1 must be equal to R2. That means this R2 is nothing but this is the angle of emergence. Okay, got it? So in the case of glass slab, what happened, your angle of incidence is always equal to the angle of emergence, right? So that will be seen here. Got it? Yes. Now let's see about the apparent depth ratio of the apparent depth and the real depth. Okay, this is very important. Okay, and it will be also there in your practical class also. Now let's take it a water, let's take it a tumbler or a what, jar. Okay, or rather you can take it as a beaker, transparent glass beaker. Okay, where you fill with water up to some certain level like this. Okay, up to some certain level like this. Then what happened, let's see, a coin is placed. Okay, a coin is placed and it is placed at the bottom and it is marked as O here. So from this O, light ray will be coming out. Okay, one slant ray, it will be coming out and emerge out in the air like this, bended away from a normal. Another ray which is coming out perpendicular to the free surface, it will go without any bending. Okay, so but if you are observing from outside this coin, then this coin seems to be raised upward. Okay, so let's take it that your eye is observing from this point somewhere here, say somewhere here, from here, then it will be seen like that this coin seems to be raised somewhere here like this. Okay, so let's see. Now this is the actual, okay, depth of the water for this coin, I mean. So we call it this as real depth, and this real depth is denoted by HR, R for real. Okay, and this is the apparent position. If you observe it from outside, then what happened, you may think that this coin O is raised, okay, upward like this, and so this will be the apparent position of the coin. This is a true position or the real position of the coin, and this will be the apparent position of the coin. And the depth from the water up to this apparent position, we call it that as apparent depth, and it is denoted by HA. Got it? Yes. Now if I'm going to take it that the angles, okay, in terms of, we are going to use the Snell's law and that, and then what, your principle of reversibility. Now you take it that this angle of incidence here as angle of incidence I. Got it? This I will be also equal to this I. Why? Because if you try to take it that the light ray moves like this, then this will be the incident ray. At this point of incidence, if you draw the normal, then this will be the angle of incidence, right? And it is denoted by I. Okay, if it is bended away like this, this I and R will be different. Now in this case, what happened, your R is greater than I. Now what happened, if you try to move backward like this from the, if you try to move backward, okay, then what happened, after reversing it, then the part, you may think that from the eye here, okay, this eye, okay, it may be seen in this way that the object O is residing here at the O prime. Now then what happened, this angle of refraction will be also equal to this angle. Why? Because these two are the normals at the same free surface. Okay, so what happened, you can take it that these two normals are the parallel lines, and you can take it these as the transversal, and so what happened, this angle R, okay, will be equal to this angle R. The angle R here and the angle R here will be equal. The angle I will be equal to the angle I here. Got it? So by using the assumption that these 2 points, the point here and the point here, these are very close actually, because when I draw it, that position of the eye, I just draw it that it may be seen from here, but actually these 2 rays must reach at your eyeball. Okay, these 2 rays, one here, another here, this must be reaching at your eyeball. Okay, like this. So this will be the black portion and this will be your pupil. Okay, these 2 rays must come out and it should reach onto your eye. So that means these 2 points, I mean this one, the point here, and this point, these 2 points are very close to each other. Okay, and so what happened, to a fair approximation, we can take it that this hypotenuse from this right triangle, okay, from this right triangle, as these 2 points are very close to each other, this hypotenuse will be approximately equal to this real depth. Okay, and this hypotenuse, the another one, okay, the hypotenuse that I'm taking here, this hypotenuse, this one, okay, from this right triangle, this hypotenuse will be approximately equal to this apparent depth. Got it? So that approximation we need to take it for this. So let's take it that your refractive index of the second medium is this one and the first medium is this one. Okay, so refractive index of second medium with respect to the first medium will be given by what? Sine of angle of incidence to the sine of angle of refraction. Got it? That is what it is given here. Okay, so next what happened for that of this next one, We can write it in this way also, BA. If you want to interchange these two, then we said that from the principle of reversibility, if you are going to interchange the position of A and B, then 1 by will be coming up as they are reciprocal. So you can interchange the numerator and denominator. Okay. Now this, how it is coming, you know that how it is coming, this one, this relation, refractive index, okay, of the second medium, okay, with respect to the first. From here it is changed like this, okay. And how this relation is coming, if you want to know it, then we can do it in a very short way. So refractive index is what? Refractive index of B with respect to A, this is equal to what? Sine of the angle of refraction to the sine of angle of incidence. Now as I told you that from this right triangle, okay, the smaller triangle, if you want to find out sine of this angle, we know that it is what? Perpendicular by hypotenuse, right? Perpendicular means this portion, let's name it as like this, let's name it as A, and this name it as point, this point as B. So your perpendicular is what? AB, and hypotenuse is what? O prime B, right? So this O prime B, as I told you that this hypotenuse and this apparent depth, these are almost same. Why? Because these A and B are very close to each other. Okay, for the sake of simplicity, I'm just drawing in a very wide way, very magnified way. Rather, this A and B are very close. So your AB and O prime B are your AB. Okay, A and B are very close to each other. So your O prime B, that means this line, okay, OB, O prime B, and this what? OA are almost same. So instead of what? Sine R, I can write as AB divided by, instead of O prime B, I can write as O prime A, right? And that one, in the case of sine of angle of incidence, instead of writing this OB, I can write as OA. So your perpendicular from this bigger triangle, right triangle, your perpendicular is AB, and hypotenuse is what? OB. Okay, so instead of OB we can write it as OA like this. So after cancelling what? AB, then this will be equal to what? OA divided by O prime A. What is this OA? OA is nothing but this is your real depth, and O prime A is what? This is the apparent depth. That is what it is coming here, okay, in this expression. Got it? In this expression I mean, right? So your refractive index of the medium or liquid with respect to air, you can say that will be equal to what? A real depth to the apparent depth. Got it? So that is what it is written here in this last statement. So what happened? Apparent depth of a number of immiscible liquid. Suppose if you are putting one oil above the other like that, okay, so there will be different layers of immiscible liquids. Then what happened? It will be the sum of all those what your apparent depth with that of its refractive index. Okay, so it will be equal to summation, means what? This will be the number of immiscible liquids. How many number of immiscible liquids? N number of immiscible liquids. So you can write that your apparent depth will be equal to summation of that of your what? Depth of the liquid with that divided by its refractive index. So if you keep on adding it, then you will get it your apparent depth. Got it? So next, let's see your apparent shift. Apparent shift means how much it has been shifted, okay, how much it has been raised. We call it that as apparent shift. So it will be nothing but it will be the difference of this real depth and the apparent depth. Got it? Yes. So that is what. So this relation will give you the apparent shift. Okay. So your apparent shift height apparent depth, real depth to minus apparent depth, the difference, this will be equal to this one. Okay, so after knowing your real depth, after knowing your refractive index of the liquid, you can easily find out the relation of the apparent shape with that of the real depth and in terms of refractive index of the liquid. So that is all about for today. Thank you and have a nice day. Okay.